Hello everyone. This is surface of possible states. Okay, for the ideal gas. Okay, this is the equation of state of the ideal gas. Okay, this is the equation of state of for the ideal gas. For real gases, the ideal gas or perfect gas same. Ideal and perfect gas are same. Okay, some books are referred ideal, some referred perfect. Okay, same. The real gases are in real life gases. Okay, so the gas we breathe are all real gases. The ideal gases are they are not exist in our world. It is imaginary. Okay, okay. So they deviate from the ideal gas law. Okay, so we can derive different equations for different by introducing different factors. Okay, the one is the compressibility factor. By introducing the molar volume of the real gas, we can derive for the equation of state of the real gas. Okay, and the other method is this is the compression factor for the real gas, hydrogen, ammonia, and methane like that. Okay, the second method is virial expansion. Okay, so here the compression factor is expanded okay, so here when pressure is zero, we the volume become infinity. Okay, when the volume becomes infinity, then only the pressure goes to zero. Okay, large volume, there is no pressure at all. Okay, then V infinity means these two are cancel out, and we get the real gas or perfect gas law. P bar is equal to RT. Okay, so this is ideal gas law. Okay, so the real equation is one of the form to derive the for real gas. Okay, the third is most important is the Wondrous equation of state. Okay, so here we explain in detail. Okay, first we take so here the repulse interaction between the molecules are taken into account. Okay, so that the molecules behave small but impenetrable spheres. Okay, so instead of moving in a volume V, they are restricted to a volume of NB. Okay, so this is the total volume of the molecule themselves. Okay, so total molecules. Okay, these are repulsion factor. Okay, so V is the repulsion factor, N is the number of moles. Okay, so we minus the volume from the total volume because they are like hard spheres, so it impenetrable. So you minus the NB from the total volume. Okay, then attraction factor when it comes to okay, the present depends on both the frequency of the collision with the walls and the force of each collision. Okay, uh, both the frequency of the collision and the force are reduced by the attraction interaction. Okay, so frequency of the collision and force are reduced by the attraction interaction. So the strength proportional to the number of interacting molecules are therefore molar concentration. Okay, so these are reducing the pressure. Okay, so that's why we minus the n square by n by v is the molar concentration. Moles per volume is the molar concentration. Okay, two factor, one force, then the frequency of collision. Two factors are there, so that's why n by v into n by v is equal to n by v the whole square, and a is the attraction factor. Due to attraction, the pressure is reduced. Okay, so this is the Wondrous. This is most important equation. So most of the questions from gas laws are from this Wondrous equations. Okay, we see the questions in later slides. Okay, if you see this is volume. Okay, when you take the n outside and cancel out, you get the molar volume like equation this. Okay, you forgot sometimes the questions they just refer to V. Okay, by V minus B, but this is molar volume. This is molar volume. Bm means molar volume. This is different from volume. Okay, you should know the difference. Okay, here the molar volume square. The V molar volume is nothing but V by N. Okay, and that is molar volume. Okay, So this is the surface. We first we saw the surface of possible states of the ideal gas. Here the surface of possible state by van der Waals equation. Okay. Um, so you see the curve are below the like loop like system. Okay, that is these are temperature, but here they are not normal temperature. They are critical temperature. Okay. Mm. So we see what is critical temperature in later slides. Okay. So what are the main features of the van der Waals equations? Okay. The perfect gas isotherm can be obtained at high pressure and larger molar volume. Okay. So when the temperature is high, RT is high. Okay. So the first term in the equation is higher than the second term. Attraction is very less. When the pressure is high and the molar volumes are large, when the pressure is high, the first term exceeds the second, so it simultaneously leads to the perfect case law. Like that, where the molar volume is large in the sense that it is larger than the B, then the below V bar minus B is equal to V bar. So we are at that time also he get the perfect case equation. Okay. uh, uh, you should know the questions may ask when the van der Waals equations are reduced to perfect gas equation. Only when high temperature and the larger molar volume. Okay. Then liquid and gases are coexist when the attractive and repulsive forces uh, are same. Okay. The van der Waals loops occur when both terms in the equations are similar magnitude. Okay. When the first term arise from the repulsive interaction, the second term arise from the attractive interaction. Okay. The critical constant, how the critical constant related to the van der Waals equation. So we see the isotherms. Okay. So here this is the isotherm. When T by Tc means critical temperature. Okay. When T by Tc equal to 1, this is the 1. Okay. So this is the critical isotherm. Okay. When the T is less than Tc, critical when the temperature is less than critical temperature, the critical temperature is you see in phase diagram also. Okay. The what is critical temperature, because below this temperature you cannot liquefy a above this critical temperature you cannot liquefy a any gas. Okay. You cannot liquefy it. Only below this critical temperature you can liquefy a gas. Okay. It is critical temperature. Okay. So you see elaborately in the phase diagram. Okay. So you don't need but first you don't need to muck up these all these things, just understand how they come related to okay. So you see this is the curve. Okay. So when you see the mathematics, in the mathematics, if you have a curve, the first derivative is the tangent to the slope. Okay. That is the first derivative. Okay. I'm not drawing perfectly. Okay. So take graph. Okay. Take this like graph. Okay. And tangent. Okay. Tangent. Okay. This is tangent. This is the first derivative. Okay. um, and the second derivative is something like, so you should you see the mathematic videos, then you better understand what is first derivative of the graph and second derivative of the graph. Three brown, one blue channel, like okay, you search for derivatives and you should better understand which is first derivative and second derivative. Okay. When the curve is flat, the first derivative and the second derivative both is equal to 0. Okay. The first derivative and the second derivative are both equal to 0. Okay. uh, so using that we calculate the critical constant. Okay. So differentiate two times the equations. Okay, first differentiation gives this. Okay, simple differentiation, dp by dvm, molar volume, differentiate with respect to molar volume. Okay, so the below vm by v, you know the formula. Okay, the power 1. Okay, so going to minus 1, so minus 1 here come to here, and minus 1 plus minus 1 is equal to minus 2, they come to plus 2. Okay, below the plus 2. Okay, so simple differentiation, if you differentiate it, you get this. And a second differentiation also 0. Okay, this is a second derivative. Okay, so the solution to this equation is this. Okay, so if you know the mathematics, you all know. If you don't know, don't worry about it, just to mark up these constants. Okay, and try to understand how it come from. Okay, okay. And this is the critical compression factor. Okay, what is principle of corresponding states? Okay, we saw what is critical constant. Okay, the critical is constant for different gases. Okay, it is vary from different have different values for different gases. Okay, so what is reduced variables? They, in physical chemistry, most of the variables are using in the reduced concept. First we saw the reduced mass, reduced atomic mass, or reduced molecular mass, like that. So because we need a dimensionless quantities. Okay, so then here molar volume, here volume, here the volume. Okay, the constant one, they cancel, the units are cancelled, and we get a dimensional numbers. Okay, so then only we can easily plot the graph. Okay, if you have a dimensional and units, you cannot plot. Okay, plot in a graph. Okay, you should know unitless number to plot in a graph, and to get a straight line or curve to interpret the graph, like that. So then this is easy to reduce. The reduced constant is simple. The actual variable divided by the critical constant is the reduced variable. The problem may ask, what is the principle of corresponding state? Means when the real gas at same reduced volume and same reduced temperature exert the same reduced pressure. Okay, this is the principle of corresponding states. Okay, here some of the reduced variables. Okay, for nitrogen, methane, propane, and ethane, this is compression factor versus reduced pressure. Okay, you plot, you get the graph like this. You already see the compression factor graph. Okay, in the previous slide, the same, but here we mentioned the reduced constant. Okay, that is the difference between they well matched with the curve. Okay, the formula, one formula is asked in the critical constant of argon and carbon dioxide. They give the critical constant and they ask the pressure and temperature. Okay, the formula is simple. Okay, so you know the critical constant, then you can easily interpret the pressure and temperature. Okay, the questions, compared to C2H6, the value of van der Waals constant A and B for helium will be. Okay, the question is simple. Okay, so we already told the van der Waals constant A is attraction, B for repulsion. Okay, so compared to the C6H6, helium is very small. Okay, so the attraction also lesser, and the repulsion also less. Okay, so both will be lesser. Okay, if you want the accurate value of this, refer the Atkins physical chemistry. At the back of the cover, back of the book, you get the all constants. Okay, you can check. Okay, simply you can A is attraction constant, B is the repulsive coefficient. Okay, repulsive coefficient. Okay, van der Waals. Okay, then this question. So at the temperature T, the fugacity coefficient is given by fugacity. It is nothing but a pressure. Okay, real gas. For ideal gas, you use the pressure P. Okay, for the real gas, you should use the fugacity. Okay, some coefficient. This is the fugacity coefficient. Okay, because the real gas always not always match with the perfect gas. Okay, so for perfect gas, where pressure is very low, fugacity equal to P. When P tends to 0, when pressure goes to 0, the fugacity equal to pressure, real gas pressure. Okay. So here you see. So this is in the Atkins deeper look. Okay. So in the Atkins, they give the materials in online. So search in the website Atkins 11th edition physical chemistry, and you see the chemical deeper look and study the fugacity. Okay. So you should understand better the fugacity. So this is the formula. Okay. To solve the problem. Okay. To solve this problem. Okay. Here the Vm is the molar volume of real gas. The Vm is the V perfect is the molar volume of the perfect gas or ideal gas. Okay. So this is the fugacity coefficient. Pi is the fugacity coefficient. Okay. We already told the here the pi is fugacity coefficient. F is fugacity. P is pressure. Okay. So they give the equation of state. Okay. They give the equation of state. P is equal to V bar here V bar, they don't put the bar. Okay. V bar minus B into RT, okay, equal to RT with B a constant. Okay. They say B is a constant. Okay. They asked the question fugacity coefficient. They asked fugacity. This is the fugacity when the equation of state is the compressibility factor. Is that means compressibility factor. Okay. Here they give the equation of state B is equal to V bar minus B into RT. Okay. So this is the they give the equation. So slightly modified. You undergo P below. Okay, then minus B become plus B. Okay, this is the V bar. We get the V for the real gas. They give the equation of state. This is the equation of state. Okay, for ideal gas, equation of state is PV bar equal to RT. Okay, so don't forget it. For the compressibility factor, PV bar equal to ZRT. Okay, ZRT. It is using compressibility factor for the real gas. Okay. Here they give the equation of state for the some imaginary, okay, hypothetical or real gas. They give the equation of state. So you should put that molar volume in the equation. Okay. So perfect gas molar volume is simple. PV bar is equal to RT. So V bar is equal to RT by P. Perfect gas. So the given molar volume is we derived it simple. P into V bar minus B is equal to RT. uh, P below. Okay, so simple mathematics. RT by B is equal to V bar minus B. V bar is equal to RT by B plus P. Okay, here the so substitute these two equation in the this formula, you get this. So you get this RT by B bar RT and RT by B. So RT by B, RT by B are cancelled out, and the B is a constant. So you can take an outside the integral. Okay, and integral of dP is equal to P. Okay, integral of dP is equal to P. So this is the equation. This is ln P. Okay, though this is ln P. They ask the fugacity coefficient. Okay, so ln means ln is nothing but if you take to e power both side e power, it gives the e power BB divided by RT. So watch this channel, 3 brown 1 blue channel. Okay, so they give better explanation for the how the ln become E and like that. So simple mathematics. So you should understand better mathematics here. Okay, you refer this channel. Okay, fine. Okay, so here the simple calculation is okay. The fugacity of a gas depends on pressure and the compressibility factor. They give the relation. So this is the equation. When the real gas equation of state is compressibility factor, then this is the formula. Okay. They most of the gas at temperature T and up to moderate pressure. The equation so they give the equation. Okay. I told the deeper look. Okay. So try to understand this. Okay. When the temperature is zero, okay, when the temperature is zero, tends to zero, temperature is when become very low. uh, this is pi equal to F by P. Okay. Okay. When the temperature is very low, then the automatically the gas molecules want to try to stick one another. Okay. So then when the attractions are dominated, okay, when the temperature is very low, attraction are dominated because there is no energy to move out of one another. Okay. So when the temperature is low, they tend to stick one another. So the fugacity is the pressure when they stick on another, the attraction increases, the pressure decreases. Because pressure is a collision between the wall. Okay. So when the attractions are increases, the pressure decreases. Okay. So the fugacity is less than the ideal pressure. Okay. This is the correct answer. The others are not. When the temperature becomes infinitive, the fugacity is greater than the pressure. Okay. Because the you supply infinite temperature means we give more energy, so the molecule vibrate more fastly and they repel each other, and the pressure is more than the real pressure. Okay, ideal gas pressure. So I already told that you try to read this very slowly and try to understand this. Okay, so if I can told you, but you forget it, and it was somewhat simple concept only. Okay, so when the when the z is nothing but z is v m by v perfect ideal v ideal. Okay, ideal molar volume, this is real volume. Okay, real volume. Okay, real molar volume divided by ideal molar volume is the z. Okay, so up to when moderate pressures, the molar volume of real is simple. Okay, so when the pressure is low, the molecules tend to stick together. Okay, so they stick together. That's why the volume is less than the ideal volume. Okay, so the compressibility factor is less than 1. Okay, and then fugacity is so you see the equation here, you see this equation. Okay, here this is the equation. So this is the compressive factor. When it is less than 1, the integral become negative and the pi become less than 1. Okay, pi become less than 1. Pi become less than 1 means uh, fugacity is less than p. Okay, pi become less than mean, so you should know that these relation z, what is z, and when z less than 1, the integral become negative. When the integral become negative, the pi become less than 1. When pi become less than 1, fugacity become less than pressure. When fugacity is less than pressure, the gas stick together. Okay, that is concept. When the opposite happens, when the z are greater than 1, this value is positive, the pi is greater than 1, and here greater than 1 means fugacity is greater than pressure, just opposite. Okay, so if you read slowly, you will understand this. Okay, okay, so here the one question, they give the van der Waals constant a, b and r, they asked the pressure. Okay, they asked the pressure. Okay, simple calculation. The given a, b are given, and the van der Waals equation, this is the van der Waals equation, just to put. Okay, so 1 liter is equal to 1000 ml is equal to 1 centimeter decimeter cube. Okay, you should simply put all the variables with the with the unit. Okay, so the unit is very important. mm, Moles, 1 you should represent the mole. You can don't need to put the 1, but you should put the mole. Okay, otherwise you missing something. Okay, here also the moles, this is n r, this is r, this is t temperature, and this is v, they give the v, and n uh, b they give the value of b. This is a, this is n square. Okay, n square means mole square. Okay, they divided by v square. Simple mathematics, and if you substitute all the units are important, you cancel all the units, here bar, here bar, you get the answer 65.3. Okay, In the key they give 62 66. Okay, so the answer is correct. Okay. Here, so this is somewhat interesting questions. Okay, so if you see this video in YouTube and just pause the video and try to understand the answer this question, and then watch the answer. Okay. So okay, here they give the ideal gas expands by following an equation. So I already told you that every word is very important. The ideal gas expands and follow the equation. In which case expect heating. Which case expect heating. Okay, and this is June 2011 question. Okay, here they give the value. The option is A between you should know A is greater than 2 less than 3 not equal. Okay, so if put equal means it is 3, it means they don't put the equal. Okay, means it's somewhat between 2 and 3, maybe 2.5 2.6 like that. Okay, so this is the options. Okay, so here also somewhat 1 to 2, here somewhat 0 to 1, here somewhat -1 to 0. In which case one should expect heating? So that is the question. Okay, so this very interesting question. Okay? I take more time to solve these questions. So I suggest you should also take time to solve these questions. Okay. Okay. I already told the answer. Okay. So when P V equal to constant, okay, when you put whatever positive value here. Okay. Say so take first example. Somewhere 2.5. Okay. Okay. Yeah, some value. Okay. If it expands, if it expands, the volume decrease. Okay, PV is equal to nRT. Okay, when the when expands 2.5 means it expand 2.5 times. Okay, 2 means it expand 2 times. Okay, 3 means it expand 3 times. Okay, like that. 2.5 means it expand 2.5 times. Okay, uh, when the volume expand, the pressure decrease. When the pressure decrease, automatically the temperature also decrease. Okay, the all positive values are like that, only they decrease the temperature. Here the negative value, when you put the negative value -1 to 0 means -0.15, you take the value -0.5. Okay, then what happens? P equal to 1 by V, 1 by 0.5. Okay, here the 0.5, here constant. Okay, here when volume increases, the pressure decreases. Okay, I'm also confused with the answer. Okay, pressure decreases means you should know temperature also decreases. Okay, so I already told you this is very interesting question. Um, oh, sorry. The math. Yeah, I made a mistake in mathematics. Okay, it does not come like this. Okay, sorry. PV power -0.5 equal to constant. Okay, so P by V whole power 0.5 equal to constant. Okay, sorry. Okay, they go if we come here below, they like 0 point minus 0.5, not plus point. Okay, So here the okay. So here when volume increases, the pressure decreases. Okay. So okay. P equal PV power minus 0.5 equal to constant means P equal to V power 0.5 into constant. Okay. Here volume increases, pressure increases, and simultaneously PV is equal to nRT. Okay. So temperature also increases. You understand? This is the minus 1 to 0. Okay. Minus 1 to 0, you take a value minus 0.5. Okay. Any value. Okay. If you the minus 0.5 become below the and when c by v power minus 0.5, the minus 0.5 when go up, they go to the v power 0.5 into constant. Okay. Here now when the volume increases, the pressure also increases, the temperature increases. So the right answer is B. Okay. Okay, so the fugacity coefficient. Okay, when the high pressure, the real gas greater than the 1. The fugacity coefficient of a real gas is greater than 1. Okay, correct. Okay, so when the pressure is high, the fugacity coefficient is greater than 1. And the fugacity is greater than 1 means this is what F by B is greater than mean is fugacity is high. Uh, because the repulsive overweights. Okay, the high temperature repel overweights the attraction terms. Okay, this is the correct answer. Okay, thank you.